The automatic night light circuit has been designed many times, usually with a variable resistor. What if we want better control over the general function of the circuit? What if we want the lights to turn on at specific resistance level of the LDR? Can we decide how much control we can have on the voltages and current at every node on the circuit? Yes, and that we will do. So if you're interested in understanding the LDR and transistors further, do watch till the end. So we have a circuit here which we will work with. If we take out Q2, R4 and R2, we'll realize we have a simple transistor circuit lighting up an LED. We have all A's connected to the 9 volts power supply. So let's find R3 and R1. If we look at the path, node A to node D across the resistor, the LED, the transistor, down to the negative, and we try to solve the voltages across this circuit, we'll have this. We have ignored the transistor because we're considering it in its closed state. So the voltage across it would be as small as we can assume it to be 0. So we have the equation for the voltages to be 9 volts from the 9 volts power supply minus VRO3 minus VLED. And of course, we know this is coming from the fact that in a series circuit, the voltage from the power supply is shared amongst the components of the circuit. So if we sum up all the voltages across the components in the circuit, it should give us same voltage as the power supply, which means if we subtract all the voltages across the components in the circuit from the voltage of the power supply, we would have 0. And our VLED in this case is 3 volts because we are going to be using a 3 volts LED. So we bring that into the equation and we have 9 volts minus VRO3 minus 3 volts equal to 0. If we make VRO3 substitute the formula, we have that VRO3 equals 6 volts. Next, we try to find our resistance from the formula V equal to IR. Okay, we have our voltage across R3 and then I, the current flowing through the circuit. Since this is a series circuit, the same current flows through every component in the circuit. So the current flowing through R3 will be the same current flowing through D1, the LED. So if we know the value of current flowing through the LED, it's the same current flowing through R3. And in this case, it's our responsibility to fix the current flowing through the LED because we want it to have an extended lifespan and not a short one. So we would limit the voltage through this 3 volts LED to be 20 milliamps. Okay, and if we put that into the equation, we would have 6 volts divided by 20 milliamps, and that would give us 300 ohms for R3. Now we have 330 ohms available, so that's what we'll be using for this circuit. But then we need to find out how much current will actually flow through the circuits if we use a 330 ohms resistor instead of 300 ohms resistor, and that would give us 18.2 milliamps. Okay, so if we go ahead to find the power that will be dissipated by R3, so we know what wattage of resistor to use. We'll see that we have 109 milliwatts. Okay, if we use the formula P equal to IV, we multiply the current, which is 18.2 milliamps, by the 6 volts across it. We're going to have 109 milliwatts. If we double that, we have 280 milliwatts. Okay, so this means that we can use our 250 watts resistor, which is the 1/4 watts type resistor here. So our resistance for R3 is 330 ohms and 250 milliwatts resistor. So we do same for the next circuit, so we can find R1. So we have the 9 volts power, voltage drop across R1 and VBE. If we isolate the circuit, we have this. But first, we remember our ILED is 18.2 milliamps. That's the current flowing through the LED. We're using a 2N222 transistor. So we remember from a previous video which we have done, okay, about transistors, that the HFE we would love to take for the the 2N2222 transistor to ensure saturation is 20. So if we bring in the formula for IB relating to HFE, we have that IC divided by HFE will give us IB. So our IC in this case is our ILED. So if we put the value into the equation, we have 18.2 milliamps divided by 20, and that would give us 900 microamps. Next, we know that from the data sheets, for us to be at saturation, our base voltage should be 0.6 minimum. So for us to ensure saturation further with respect to operating conditions, okay, we increase that a bit. So we're adopting 0.8 volts for our VBE. All right, so if we do so, we would see we have VRO1 plus VBE to be equal to 9 volts, which is the voltage from the power source. Okay, so making VRO1 the subject of formula, we have 9 volts minus VBE, which happens to be 0.8. Okay, and that would give us VRO1 as 8.2 volts. So now we have VRO1 as 8.2 volts, and we have IB as 900 microamps. So let's find out what RO1 actually is, the resistance value of RO1. For that, we would have to divide 8.2 volts by 0.9 milliamps, and we'll be having 9.1 kilo ohms. Okay, and that resistor value is available, so we would be using that. So let's also find the power rating, or the power that resistor is going to be consuming, operating with 8.2 volts across its ends and 900 microamps flowing through it. Okay, so if we do that, we would find that our power is 7.38 milliwatts. If we double down on that, we'll be having 14.76 milliwatts, which means we can also use the 1/4 watt type, which is 250 milliwatts. So our resistor for RO1 is 9.1 ohms and 250 milliwatts power rating. So now let's bring in our transistor controlled by the LDR. If we extract the circuit, we would have this. So we need to find R4, but first we have a 5528 LDR, and when it's totally dark, its resistance is 1 mega ohm. So I'll set my space to a fairly dark situation, the kind for which I will want my resistor to turn on and read off the resistance of the LDR, and I get 500 kilo ohms. So if we want our LED to light up at approximately 500k, we will need 0.6 volts at the base of the Q2 transistor when the LDR is 500k, and this is because below 0.6 volts at the base, the transistor turns off. So we know that when it's totally dark, we have 1 mega ohms. So we need our lights to be on at 500 kilo ohms. So if we try to solve the voltages across this circuit, we have 9 volts minus VRO1 minus VBE. And we know we want VBE to be 0.6 volts at 500 kilo ohms. So we solve for ILDR, okay, by bringing it into the equation. So we have 9 volts minus VRO1, which is same as our VLDR, okay. We would change that to 500 kilo ohms times ILDR, okay, which is voltage. Of course, voltage is current times resistance. So we subtract that from 0.6 and we try to make ILDR subject to formula. So we're going to be having 9 volts minus 0.6 divided by 500 kilo ohms, and this will give us an ILDR of 16.8 microamps. So looking at this circuit, we'll see we have current flowing through this resistor, and then we have current coming to this junction. It will have to split into 2 parts, okay. Some will flow through RO4 and others will flow through VBE. We have to decide how much current we want RO4 to sink, all right, and we have to make it most of the current, because at this point where this voltage is 0.6, we want that to be the point where our light turns on, which means the current flowing through VBE should be minimal. All right, so at other resistances, the current through VBE would improve, okay, to let the LED turn off. All right, and that would be because we have enough light that would reduce the resistance of RO1 to let current flow through. But at this point, which is array LDR of 500k, we want to be sure that minimum current flows through VBE, because we are about to turn off the transistor to enable the light come on. And in that case, we need majority of the current flowing through R4. That's majority of the 16.8 microamps. So we would decide to sink 12 microamps through R4. And in that case, we would have our IB to be 16.8 minus 12, which will be 4.8 microamps. So we're going to have 4.8 microamps flowing through IB. Of course, we have 16.8 microamps coming here, and we have 12 microamps coming here. So we'll be left with 4.8 microamps for VBE. And so we can use the equation V equal to I arrow to find R4. So if we do that, we would have R4 to be equal to 50,000 ohms. What we have available is 51,000 ohms, and that's what we'll be using. And if we put that into the equation to find what current we would have through R4, if we divide 0.6 by 51 kilo ohms, we'll have 11.8 microamps. And if we find the power for this, of course the power is going to be very little. We have 0.6 volts times 11.8 microamps, which will give us 7 microwatts. Okay, we double that, we have 14.16 microwatts, and that will mean we'll have our R4 as a 54 kilo ohm resistor and 250 milliwatts. So if you followed what we did meticulously, you should have this, and the switch off and on of the light should happen at about 550k ohms. So what you can do is put another LDR very close to this one on the breadboard, not connected to the circuit, but just so you can read off the resistance value of that particular one to know exactly what the resistance value of this one in the circuit is. Because if you read this one while it's in the circuit, you might have a wrong reading because of other resistances in the circuit.